Hi, so for today we're going to talk about nodal analysis. This is still a part of our discussion all about the circuit theorems in DC analysis, DC circuits. So let's get started. So for today's video, we're going to solve two problems involving nodal analysis. So here are the steps to determine node voltages. Okay. So for number one, how do we do nodal analysis? So select a node as the reference node. So for example, in this problem, we have nodes 1 here, okay, and node 2 here. So we have node 1 here, node 2 here. So that is actually what we call the reference node, okay, of which those nodes we need to determine the voltages at node 1. Okay, as you can see, this is the voltage, okay, the reference node, and the voltage at node 2. So assign voltages V sub 1 for each node. V sub 1, we have V sub 1 for the node voltage here, V sub 2 for the node voltage here. So a node is actually a point where we have three or more components connected. Okay, so we have for the node 1, we have the 2 ohms, 4 ohms, and then the current source 5 amperes. And for the node voltage or the node 2, we have the 4 ohms, 6 ohms, and the 10 ampere uh, current source. So if we have already assigned the voltages, node voltages, we have V sub 1 and V sub 2. Apply KCL to each of the n minus 1 non-reference node. So use Ohm's law to express the branch current in terms of node voltages. So we will be applying KCL on each node. So we will be analyzing what are the current entering and what are the current leaving, okay, in this node. So for number 3, solve the resulting simultaneous equations to obtain the unknown node voltage. So the very first thing that we are going to do, we have already a node voltage V sub 1 and V sub 2. So we will proceed to number 2, wherein we will be applying KCL, okay, in each node that we have. So by that, we mean that we will be analyzing all of the currents entering and leaving this node 1 and node 2. So it is very obvious that we have a 5 ampere here, okay, that is entering the node. Let us label that's 5 ampere as I sub 1, okay. That is the 5 ampere here entering the node. And then we have also, okay, if we are going to analyze, we also have a current in this direction. So we have I sub 2. We can assign that. We have I sub 2. And we have in this direction, I sub 3. Okay, so that it would not be confusing. Okay, so we have an I sub 1. We have I sub 2 and I sub 3 here. Okay, that current that flows here. So take note that this I sub 2 is not the same with I sub 3 because we don't have uh, the same resistances. Okay, so in the case that we have the same resistances, most probably they have the same uh, current. So we label it. Okay, we label this I sub 2 in this direction, and we should assume always that the current flows from the higher potential V sub 1 to a lower potential V sub 2. Again, the current flows from the higher potential to lower potential depends on the flow of current. So meaning this is the higher potential minus the lower potential. So we have also uh, the 10 ohms. So we have 10 ohms here. We labeled it as our I sub 4. I mean 10 amperes. I mean this current source. So we have I sub 4 here. And we can have a current here. We have I sub 5. Let's call it I sub 5. Okay? So we don't know the currents. But as I have said, after we have already defined the current for each node, okay, it's time to use KCL. So if we're going to use KCL, okay, KCL at node V sub 1 or node 1, okay? So we must apply KCL there. So again, current entering is equal to the current leaving. So the current entering at node 1 would be I sub 1 that is equivalent to the current leaving, which is I sub 2 plus I sub 3. Now, we will be expressing this in terms of voltages by Ohm's law. I equals V over R. So the I1, since it is already a current source, so we have the value of I sub 1, that is 5. Okay? And for I sub 2, it passes from the node voltage 1 and node voltage 2, okay, by this 4 ohm resistor. So basically, what are we going to do is, since the current flows from the higher potential, that higher potential is this node voltage 1 and lower potential is this voltage 2. So therefore, we have V sub 1 minus the V sub 2 all over 4. So as you can see, we have V sub 1 as the higher potential, so that's why it's positive. We have V sub 2 as negative because if we track the sign of our current here, so it current flows enters from the higher potential to the lower potential, so that we have V1 minus V2 all over whatever resistor value the current goes through. So we have V sub 1 minus V sub 2 plus we have I sub 3. I sub 3 is simply, okay, the voltage at 1, okay, by Ohm's law all over 2 ohms. Okay? So if we are going to multiply this by 4, okay, to actually um, simplify this, so we have 20 equals V sub 1 minus V sub 2 plus 2V sub 1. So we have already multiplied by 4 so that we can simplify it. So we have 20 V sub 1 plus 3, 2V sub 1 would be 3V sub 1 minus V sub 2. Okay, so rearranging, we have 3V sub 1 minus V sub 2 equals 20. So that is our first equation. So take note that we need two equations because we have two unknowns which are V1 and V2. So if we have KCL at node V sub 2 or node 2, okay, so analyzing all the currents entering equals current leaving, okay? So we have a current entering at node 2, I sub 2 and I sub 4, okay? So we have I sub 2 plus I sub 4. And take note also that we have I sub 1 here, leaving the node 2, okay? Because if we are going to track the direction of this 5 ampere, so it came from here, okay? So that we have I1 also here and we have I1 also here. So current entering is equal to the current equals current entering equals current leaving. So we have I sub 1 plus I sub 5. So as you can see, I sub 2 entering I sub 4 equals to the current leaving I sub 1 and I sub 5. Okay? So for I sub 2, we have already have the formula. So that is V sub 1 minus V sub 2 all over 4. If you're going to track this. And then we have plus I sub 4. Our I sub 4 is 10 amperes. Okay? 10 amperes equals I sub 1, which is 5. Okay? 5 amperes, that's our I sub 1, plus I5. So I5 would be V sub 2, node voltage 2, okay, over the 6 ohms. So if we multiply both sides by 12, so that we have a simplification, we have 3 V1 minus V2, okay, plus we have 120, okay, equals 60 plus 2 V2. So if we rearrange this, we have 3V1 minus 3V2. Okay, transpose this. So we have negative 2V2 here. And we have 60 minus 120. So we have 3V1, okay, minus 5V2. Then we have negative 60, I mean. So we have negative 60. Okay. Negative 60 here. So this is our equation 2. And as you can see, okay, equation 1 and equation 2, if I multiply or subtract, okay, equation 1 from equation 2, this would be cancelled. V1 would be cancelled. So we have 3V1 minus V2 equals 20. So minus equation 2. So we did is equation 1 minus equation 2. That is what we did. Okay? So we have negative 3v sub 1. Since this is a minus, the minus would be distributed. So we have 5v sub 2. Then we have negative of negative would be 60. Okay, and then proceed to addition. Okay? So we distributed the minus sign so that this become negative. And then we can see that this would cancel. And then we have 4v sub 2 equals 80. Therefore, V sub 2 is 20 volts. Okay? The node voltage at that point, V sub 2, okay, is 20 volts. So how do we get the remaining node voltage? Okay? Node voltage V sub 1. So from, okay, we can either solve from equation 1 or equation 2. So we can solve from equation 1 since we know already the value of V2. So we have 3v sub 1 minus v2 equals 20. So you have 3v sub 1 minus 20 equals v sub 2. So v sub 2 would be 3v sub 1, okay, minus 20. So v sub 2 is 20, okay, plus 20 here. I transpose this. So we have 3v sub 1. So we have 40 all over 3 equals v sub 1, or in other words, that will be 13.3333 volts. So that is the node voltages, okay, that v sub 1 and v sub 2 using the nodal analysis. So it's pretty much easy. Just as you are going to assign, so the flow of the current here, okay, and you have to have a very careful in writing the KCL equation. So we have the, again, okay, we have first select a node, V sub 1 and V sub 2, and then we apply KCL in each node, and then we solve the simultaneous equations to obtain the unknown or the unknown node voltages V sub 1 and V sub 2. Okay? So, that's it. So, let's try another example. Okay? So, for example, we have this circuit again, and we're going to solve the all of the node voltages. We have V sub 1, V sub 2, and V sub 3 here. Okay, since we have already an assigned direction of current for node voltage 1 to voltage 2, Ix, I sub x, so it is fixed. We cannot assign the current arbitrarily for that. So we have, in this direction, we have to have 3 amperes. Okay, that is our direction entering this node. Of course, if there enters a node of 3 amperes here, leaves the node I sub x, so definitely there will be a current here, okay, in the 4 ohms, and that is what we call I sub 1. Okay, so again, this would still be I sub x, okay, I sub x that is entering this node 2, and we have an I sub, let's say, from 2 to 3, okay, we have also a current that is I sub 2, okay, and then what are we going to do is for this 4 ohms, we have I sub 3, okay, so analyzing also in this node, we have I sub 2 still, and we have I sub 1 entering this, the current from here, okay, and then we have a dependent current source to I sub x, of which this current source depends on the value of I sub x here. So we have already assigned. So if we have KCL at node 1, okay, that is our node voltage V sub 1. So current entering equals current leaving. So we have 3. Current entering is 3 amperes. That is equal to the sum of the current leaving the node. So we have I sub 1 plus I sub x. So we have I sub 1 plus I sub x. So by Ohm's law, so we have to express this in terms of node voltage, V over R. So I sub 1, we have from node 1 to node 3, so we have the potential at V1 minus the potential at V3. It passes through 4 ohms, so we have V sub 1 minus V3 all over 4. Okay? So potential at 1 minus the potential at 3, Okay, all over the 4 ohms. And then we have I sub x is V sub 1, potential at 1 minus potential at 2. All over we have 2. So we multiply this by 4. So we have 12 equals V sub 1 minus V sub 3 plus we have 2V sub 1 minus 2V sub 2. I already distributed the 2. Okay? So we have 2V sub 1 plus V sub 1 is 3V sub 1. Then we have 2 minus 2V sub 2. Okay? And then we have minus V sub 3 also equals 12. So we have the first equation. So by the way, we will be having 3 equations because we have 3 unknowns here. So that is our KCL at node 1. So how about KCL at node 2? Okay? So how do we do that? If we have a KCL at node 2, current entering is Ix equals current leaving. Okay? So we have I sub 2 plus I sub 3. Okay? Ix, we have already have that. So we have V1 minus V2 all over the 2 equals I sub 2. We have I sub 2 passes through the 8 ohms from voltages, node voltage V sub 2 and V sub 3. So we have V sub 2 minus V sub 3 all over 8. Okay, and then we have the current leaving plus the current leaving I sub 3. So we have V sub 2 all over 4. So if we multiply this by 8, so we have 4 V sub 1 minus 4 V sub 2 equals V sub 2 minus V sub 3 plus 8 over 4 is 2 V sub 2. Okay, if we are going to evaluate this, simplify 4 V sub 1, we have minus 4V sub 2. So we have 2V sub 2, 3V sub 2, 2V sub 2 plus V sub 2 would be 3V sub 2. Transpose it, so it becomes negative 3V sub 2 plus V sub 3 equals 0. So we have 4V sub 1 minus 7V sub 2 plus V sub 3 equals 0. So that is our second equation. And how about for the third node? Okay, so we have KCL at node 3. Okay. So current entering is I1 and I2. So we have I1 and plus I2. So we have I sub 1 plus I2. Current leaving is 2IX. Okay. Okay. But IX, we know that IX will be V sub 1 minus V sub 2 all over 2. So we have already the value of I1. Again, from our I1, we have V1 to minus V3 all over 4. So our I sub 1 would be V1 minus V3 all over 4. Plus, we have I sub 2, which is V2 minus V3 all over 8. So we have already written that V2 minus V3 all over 8. And then we have twice of Ix, of which our Ix is still, that is still the same current, okay, that we are actually writing a while ago. So we have V1 minus V2 all over 2. So these twos will cancel. So we have V1 minus V3 all over 8 plus V2 minus V3 all over, this would be all over 4, not 8. So we have this 4 equals V1 minus V2. Multiply both sides by 8. So we have 2V1 minus 2V3. I've already distributed the 2. Okay, so because 8 divided by 4 is 2. So multiplied by V1 minus V3. So plus we have V2 minus V3. So V2 minus V3 equals 8V1 minus 8V2. Okay, so if we are going to rearrange this, so we have 8V1. Okay, and then transpose 2v1, so we have negative 2v1. I shifted this, okay, I write this first, okay, because we have a v1 here. So 8 minus 2v1, and then we have minus 8v sub 2, which is this. Okay, transpose this becomes negative v2, and then we have negative 2v3 minus 3, minus 1, minus v sub 3. This becomes negative 3v3. Transpose it, it becomes 3v3 equals 0. So we have 6v1 minus 9v2 plus 3v3 equals 0. So they are all divisible by 3. So we can divide them by 3. So we have 2v1 minus 3v2 plus we have v3 equals 0. So now we have already completed all of the node voltages equation. So we have equation 1, we have equation 2, and we have equation 3. So you can solve it by elimination, by substitution, whichever you are confident enough. But I'm confident when using uh, Kramer's rule or matrix. So I find it much easier. So we have for the equation 2, we rewrite it as negative 7 v2 plus v3. Okay, equals 0. That is our equation 2. Our equation 3 is 2v1 minus 3v2 plus v3. Okay, equals 0. That would be my equation 3. Putting that into matrix form. So this would be 3, 4, 2. I have negative 2, negative 7, negative 3 here. Okay, and then I have negative 1, 1, 1. Those are the coefficients of v sub 1, v sub 2, and v sub 3. Remember that the constant should be on the right side. Okay, that should be equal to 12, 0, 0. Okay, so what are we going to do is first get the determinant of this. Okay, so get the determinant of this. That is our delta. So 3, 4, 2, negative 2, negative 7, negative 3, negative 1, 1, 1. So get the determinant of that by our calculator. So we have shift matrix dimension, matrix A, and then 3 by 3. So we have 3, we have negative 2, we have negative 1, we have 4, we have negative 7, we have 1, we have 2, we have negative 3, and then we have 1. So AC, shift matrix 7, determinant, shift matrix of A. So the determinant of our matrix A would be negative 10. Okay, and to get the V sub 1, so simply replace the first column with the constant and get the determinant. So we have 12, 0, 0. Then we have negative 2, negative 7, negative 3, negative 1, 1, 1. So if we get the determinant of that using our calculator, so we have shift matrix, dimension matrix A. So we have only replaced this first column. So we have 12. Okay, so we have 12. Okay, I can go on with this because it's actually the same. Okay, so we have 0 here. Okay, negative 7, still negative 7, still 1. Then we have 0 here, still negative 3 and 1. So press AC, shift matrix determinant, shift matrix of determinant of matrix A. So that would be negative 48. Okay, and in order to get V sub 1, okay, we have the formula what we have used also in super mesh, so that we have negative 48 all over negative 10, so that would be 4.8 volts. Okay, so what are we going to do to get the V sub 2? Is we have delta sub 2. We are going to replace the second column by the constant. So we have 3, 4, 2. We copy this. We will be replacing this by the constant. So we have 12, 0, 0. And then we have negative 1, 1, 1. And get the determinant of that. Again, using our calculator. So we have shift matrix dimension, matrix A. Then we have 3. We have 12. We have still negative 1. So we have 4. We have 0 here. And we have still 1. Then we have 2. We have 0. And still we have 1. So get the determinant of that. So shift matrix A, determinant of matrix A. So that would be negative 24. So to get V sub 2, that should be delta sub 2 or all over delta, which is the same delta PU. So we have negative 24 divided by negative 10. So that must be 2.4 volts. Okay. And last but not the least, we have delta sub 3 to get V sub 3. So replace the third column with the constant and copy the remaining elements of our matrix here. So we have 3, 4, 2. We have negative 2, negative 7. We have negative 3. Then we have 12, 0, 0. Then get the determinant. So again, you can use other matrix, okay, when you have a dimension. So dimension of matrix B or matrix C. So you can use also that. So we have 3. We have negative 2. Okay. Then we have 12 here. We have 4. We have negative 7 here. We have 0 here. We have 2 here. Okay. We have negative 3. And then we have 0. So let me just double check it again. 3, negative 2. Okay. 12, 0, 0. Okay. The 4, negative 7, 1. Okay. 4, negative 7, 0. That's correct. Okay. And then we have 2, negative 3, 0. Okay. So get the determinant. Shift matrix 7, determinant of matrix A. So we have a 24 answer. So to get V sub 3, that must be delta 3 all over delta. Our delta 3 is 24 all over negative 10. So that must be negative 2.4 volts. Okay. So our answers are, okay, our answers is V sub 1, it's 4.8 volts. V sub 2, it's 2.4 volts. V sub 3, it's negative 2.4 volts. So that's how we get the node voltages V sub 1, V sub 2, V sub 3 using nodal analysis. Okay, and using Cramer's rule to determine the values of the unknown node voltages. So, if you like this video, if you learned something from this video, please give it a thumbs up and please don't forget to share it with your friends, engineering friends, who are also taking up electrical circuits. So again, this is Engineer Abat. Thank you so much and God bless.